Okay, so our first circuit is this guy. Basically, a very simple application of, just a very simple application of nodal analysis and what we've been doing. So, first task is to identify all the nodes. So, there's a node here, node here, node here, and all this right here is a node. Okay? Remember, nodes are the places where connections between elements exist. This is only one node, even though it connects more than two elements together. Now we need to define one of our nodes as the ground node. So we're just going to do that with this node right here. It's going to be ground. And now we need to find the voltage at all the nodes relative to ground. So this node's easy. We're at 0 volts right here. We go through the battery, we gain 1 volt. Okay? These nodes are not as easy, so we need to do a little bit of thinking. Let's define a variable for this node, Vx. Okay? And now let's set up the KCL expression. So we know that from this current source, we have 5 amps going into there. 5 amps. Okay? We just need to find these other two currents. So we're going to say there's a current going there and a current going there. For this current, this one through the 2 ohm resistor, the voltage before is Vx, so Vx. The voltage after is 1 volt, minus 1, over the resistance. So that's the current through that resistor. The voltage before is Vx, the voltage after is 0. So the current here is going to be Vx minus 0 over 1. Then we just add those together and set that equal to 5 amps, because that's the current going in, and we have these two currents going out. So 5 equals Vx, because that's just Vx minus 0 over 1, plus Vx minus 1 over 2. We go ahead and solve this. We get 10 equals 3 Vx minus 1, or Vx equals 11 over thirds, which equals about 3.67 volts. Okay? Now, we know that there's 5 amps of current going into here. So we know that the voltage drop across this guy is 15 volts, right? V equals IR. So that means the voltage here is 15 volts higher than the voltage here. In other words, the voltage here is 18.67 volts. Okay? There's one voltage. There's another node voltage. There's another node voltage. And there's our last node voltage. Okay? Now, finally, for the power dissipated by the circuit, what you're going to do is just add up all the contributions from all the batteries and take the negative of that. So, 5 amps, remember, P equals IV, right? P equals IV. So for the 5 amp current source, I is 5, V is 18.67. So P is approximately, for that guy, about 94 watts. Plus the power here, but the power here is going to be negative, okay? Because current is going into the positive terminal of the battery. So that means the battery, this battery actually absorbs power. It's going to absorb 1 volt minus 3.67 minus 1 over 2. So that's about 1.3. So plus negative 1.3 watts. So the total power supplied to the circuit is about 92.7 watts. And you should calculate the exact number, of course. That's the power supplied. And so it's also the power dissipated, right? Power supplied equals power dissipated for all circuits. The key is remembering, since current enters the positive terminal here, this battery dissipates power. Okay? That's problem 1. Okay. So for this guy, I'm going to start using my shorthand for batteries, which is just this. The long side, so these lines are kind of short, but the long side is the plus side, and the short side is the minus side. Okay? That's just the common notation that we use for batteries. It's easier than drawing a circle for DC battery sources. So first task here, find all the nodes. Again, this is exactly the same procedure as before. Big node right here, that's actually our ground node, that's 0 volts. Another node right here, and another node right here. Okay? There's actually no other nodes in this circuit. And we already know the node voltage here is 0 volts. We know the node voltage up here is 3 volts, because it's just 3 volts greater than the node voltage down here because of the battery. And we know the node voltage up here is 2 volts, because it's just 2 volts greater than the ground node, which is 0 volts. So now we can write down the currents. We don't actually need to do any algebra for other node voltages since we already have all the node voltages solved. So the current here, voltage difference is 1 volt, 3 minus 2 is 1. 1 over 2 is 0.5 amps. Current through here, 3 over 4 is 0.75 amps. And current here is 2 over 4, which is 0.5 amps. Okay? So, there's only one other current to consider for both those junctions. How much current is here, and how much current is here. Okay? Because remember, there's only one other place where current can go in or out to this node, and same for that node. So there's 0.75, 0.5 leaving there. So actually there's 1.25 amps flowing into there. There's 0.5 going in, 0.5 going out. So actually 0 current flows here. That's pretty weird. It's like that battery doesn't even exist. So now we have all the currents. We can easily find the power dissipated by the circuit. This guy gives 0 watts, so this guy you can completely ignore. But you can't really see that. So this guy you can completely ignore. Okay? And all we have to consider is this guy, who supplies 3 volts times 1.25 amps. 3 times 1.25 equals 3.75 watts. Okay? That's that. Note that these resistors are not in parallel, okay? Parallel resistors have to drop the same amount of voltage. These resistors do not. Clearly, right? There's a different voltage here compared to there. Primarily because of the resistor. If this resistor was not there, then these resistors would be in parallel and we could simplify it. But we can't simplify that circuit. So that's problem 2. So next we have this guy. Again, nodal analysis. Exact same thing we've been doing. First find the nodes. We have a node right here. We have a node right here, we have a node right here, and we have a node right here. Okay. Next up, label the node as ground that we want to. It'll be easiest if this node is ground, so that's going to be 0 volts. We already know the node voltage here is going to be 1 volt. We already know the node voltage here is going to be 3 volts. Again, I'm going quickly, but just go through the battery, right? 0 volts before the battery. We gain 3 volts when we go through the battery, so we're at 3 volts here. Same logic for there. So the only node voltage we don't know is right here. Call that Vx. Okay? Now we know the current through this resistor is 5 amps. Okay, we know that's 5 amps because this current source forces that current to be 5 amps. So that means the voltage dropped by the resistor divided by its resistance has to equal that current. So Vx minus 3, that's the voltage dropped by the resistor, divided by its resistance of 3 has to equal 5 amps. And thus, Vx equals 18 volts. Okay? And now we've solved all the node voltages and we're done with that. Now we need to find the current and direction through each resistor. So we already know this current, the only other resistors here, and that one's easy too. 2 volts dropped from here to here. And so, current equals voltage over resistance. So, that's just going to be 2 volts over 2 ohms, or just 1 amp. That also means there's 4 amps here. Okay, and that'll be important. So now we just have to get the power, and we can just find the power supply to the circuit. So first of all, notice that these currents flow into both these batteries, okay? These batteries are actually dissipating power because it's flowing into the positive side of the battery. So this guy gives us negative 1 watt. Current is negative 1 amp times the voltage of 1 volt. This guy gives us negative 12 watts. Okay? Current is negative 4 amps times 3 volts is negative 12 volts. This guy gives us 5 times 18, which is just 90 watts. Okay? So the total current supplied to the circuit is just the sum of all these, which is just going to be 77 watts, I think. Unless I'm bad at math. That's the total current supplied to the circuit. So, yeah, this is just to be clear, this is a very not physical number. A 5 amp current source is huge. You're starting fires with that much current. In reality, you'd be dealing with milliamps and kilo ohms, right? That's much more standard. But yeah, that's that one. Alright, so up next we have this guy, which looks like a big mess, but actually it's not so bad, because we're going to simplify a bunch of these resistors. Just right off the bat, these are in series. This becomes a single 10 ohm resistor. Okay? Combine those. These are in series. They become a single 9 ohm resistor. These are in series. They become a single 11 ohm resistor. Okay? These are in series and they become a single 11 ohm resistor as well. Okay? Just like that, we've made this circuit a lot cleaner to look at. Okay? Now, again, we have to find nodes. So we have a node right here. You have a node right here, a node right there, a node right there, and a node right there. So this bottom node is 0 volts. This node is 4 volts. This node is 3 volts. But these two nodes we don't know. So I'm going to call this VA and VB. Okay? Now, we're going to write KCL expressions for each of these. So we have current going there, current going there, there, current going there, current going there, current going there. Okay. So, for VA minus 4 over 10, that's the first current, and going in that direction, right? 4 minus after divided by resistance, plus VA minus 0 over 9, plus VA minus VB over 4 equals 0. Okay? That's our first expression. Our next one is for VB. So we have, for B, it's invisible, yeah, VB minus VA over 4 plus VB minus 0 over 11 plus VB minus 3 over 11. Okay? So now you can go through, use your favorite circuit analysis technique to find, or sorry, favorite systems of equation solving technique to solve here. I guess I can show how to do it. So, to me, I see this term is exactly the negative of this term. So, adding these equations together could be a promising technique. Substitution could also be a promising technique. Yeah, actually, I'm not going to solve it here because it's just a bunch of algebra. But go plug it into your favorite system of equation solver, solve it yourself, whatever. You'll get values for VA and VB. From there, you can solve for this current and this current to get the total power supplied to the circuit. And remember, if you happen to see that current's going into the positive side of the battery, remember that means that the battery is absorbing power. Okay? But yeah. Again, it's just nodal analysis again and again and again. You see how standard. Nodal analysis is a very, once you get it, it really clicks, and you can solve all these circuits super quickly. Yeah. So that's why I really recommend it as an analysis technique. All right. So for this circuit, you have a battery sitting up here. So it's going to be a little tricky, something we haven't seen before. But again, nodal analysis will get us all the way. So First of all, this whole node right here, this whole thing is 0 volts. Okay? Another node here, another node here, another node here, right? Because it connects two elements. Another node here, and another node here. It looks like there's a lot of nodes and our life is going to be super difficult, but it's not that bad actually. Well, first of all, we know the node voltage here is 0 volts, and so the voltage here is 12 volts. We're going to call this node VA, okay? We're going to call this node VB, and so this node is just VB minus 5, okay? Right? Because we go through this battery, we gain 5 volts, so 5 plus VB minus 5 is VB. And then this node, notice how there's 5 amps of current flowing this way through this resistor, right? 5 amps going this direction. So we lose 15 volts as we go that direction. So we gain 15 volts as we go in this direction. In other words, this is, or sorry, not 15, 50. 50. Wow. We gain 50 volts as we go in that direction. So VB plus 50. Again, 5 amps is not a very physical amount of current. That's a lot of current. So actually, we only have 2 variables here to solve for. And we just, again, write out our KCL expressions. That's all we have to do. So we have current in that direction. Current, oops, I'll use green for the currents. So we have current in this direction, current in this direction, and we have current going in here. That's 2 amps. So the current going here is just VA minus 12 over 3. That's this current. Current going there is VA minus VB minus 5. So plus VA minus VB minus 5 over 2 ohms. Okay? And that's just equal to 2 amps. Okay? So we have our first equation. I'll box that in. For our second equation, we need something for VB. So we know that there's 5 amps going in here. We can also put a current going there and a current going here. And now here's the key thing to notice. We can't do like a V equals IR expression for the battery because the battery has 0 resistance. But we can for the resistor. And we know the resistor current is the same as the current of the battery. So for the resistor, it's VB minus 5 minus VA over 2. That's the current in this direction, right? Before minus after over resistance. So VB minus 5 minus VA over the resistance, which is 2, plus, down here that's easy, VB over 2, equals 5. Okay? Now we have a system of 2 equations and we have 2 variables, so you can do some algebra and solve that quite easily. Again, I'm not going to do that here because it's just too much math, but it's a simple system of equations. Then you got some value for VA, some value for VB, and then again, V equals IR. For a battery, does the current flow into the positive part? If it does, then that battery absorbs power. For a current source, is voltage gained opposite the direction of current flow? If so, then this current source absorbs power. Okay? So that is that problem. It's not as bad as it looks. Just remember, all you need to do is find each node, write the voltage at each node. That's the same prescription for every problem.